All right, so let's do section 15.1 right here. So far you've dealt with calculus functions of a single variable. And so like when you have y equals f of x, like one variable is being put in and you get one answer out. All right, so but in the real world, you have different variables working there. Maybe you have your like longitude and latitude, and that gives you your temperature, that kind of stuff. So there's like more inputs than just like one thing. All right. And so, for instance, like when you have the formula for the volume of a cylinder, the volume is pi r squared h. So you have two inputs to get that output of the volume, okay? And so when you have something denoted by f of x, y, your domain is x and y. So you're inputting two things, and your range is f of x, y. Or basically that's equal to z, right? So a single variable, we had f of x, and that was equal to y, right? And so here with two variables, we have f of x, y, which is equal to z. So basically the idea here is that f of x, y, z is the replacement for that, kind of like f of x was y. So it's important to note, to realize this type of function, both x and y are independent variables. And z is your dependent variable. Okay, all right. So for these things, we can also do our domain and plug stuff in. So we're going to try and plug in 3 and 2. So f of 3, 2. I would plug in 3 and 2 in the numerator. So 3 plus 2 plus 1 is 6. So square root of 6. And 3 minus 1 on the bottom is 2. So I can plug in a point just like I always have. And then doing the domain, first of all, notice that x minus 1 on the bottom. So x can't be 1. Also, I noticed on the top that inside of a radical cannot be negative. So x plus y plus 1 has to be greater than or equal to 0. Okay, so you can also draw a picture of these things. So let's go ahead and write our domain here. So my domain is any point x, y such that x cannot be 1. And let's do this. Y is greater than or equal to negative x minus 1. Let's solve it for y so we can graph it in a second. So if we wanted to, we could kind of graph what's going on right there. Negative x minus 1 starts at negative 1, goes down 1 over 1, or up 1, back 1. So that is that solid line, and I want everything above it. But I also do not want x to be 1. So when x is 1, I kind of have like a dotted line right there that I don't want to touch. So basically, I want everything greater than this line, but I also don't want to touch that red line right there in the middle. So for instance, if I was picking points, if I pick something over here, that would be okay. Something here, fine. Something over here, fine. Excuse me. But pick something on this line, no. Pick something over here in this area, no. Okay, so that way you can kind of note the domain. All right, over here, f of 3, 2. Oopsie. So I get 3 ln of, that's going to be 4 minus 3 inside there, so ln of 1. Oops. All right, so ln of 1 is 0, we all know, so that would be 0. All right, my domain, I would say to you that this part right here, y squared minus x, has to be greater than 0. You can't do log of 0, and you can't do log of a negative. Okay? So maybe we'd like to make this y squared has to be greater than x. So if I was going to do my domain, I would say give me an x and a y value, such that y squared is always greater than x. So if I'm having trouble making my brackets there, all right, so if we want to draw that little area, okay, x equals y squared is a parabola on its side, so I'm going to do a dotted one because it's not equal to here. And if I want to do like a test point, like why don't we test the point 0, 3? So if I put 0, 3 in this problem, I get 3 squared is greater than 0, which is a true statement. So that means that that point was on the side that I want. So that means everything that I want is outside here. All right, so any place in that area would be okay. It would satisfy this problem. I could like do this problem in that area. So that's kind of like where my graph will exist. Okay, only in that region. All right, if a function of two variables with domain D, then the graph of your function is a set of all points x, y, z in R3. So that means you have a three-dimensional picture. All right, so let's go ahead and sketch some pictures here. So remember, this f of x, y, that's the same thing as saying z. So I got z equals 6 minus 3x minus 2y. Hopefully you recognize if I move everything to one side, maybe even better, you get 3x plus 2y plus z equals 6. It's a plane. All right, so if I let y and z be equal to 0, I get x equals 2. So that's an x-intercept. If I let x and y be equal to 0, then I get z equals 6, so there's a intercept there. And if I let, let's see, x and z equal to 0, I get y equals 3. So it's an intercept there. So you can try and draw a little plane through those things. So you got, I don't know, like I think I'll just draw like a little triangle here. And then just kind of like show myself it's going out in, you know, every direction right there, but this is a plane. And so you could also, if you want to, kind of draw like a little rectangle there, if you want. So in two dimensions, when you have a line is like your basic function in 2 dimensions, right? Your most basic graph. So it's a linear function. So in 3D, your most basic graph is a plane. And so this function that we just did, this plane, is actually called a linear function. It's called a linear function when we're in 3D. It's basically like our basic equation in multivariable. Okay, so a lot of times you want to be able to sketch things and see what's going on because we're going to have to be doing derivatives and integrals with these things. And so we're going to tell the domain and range. So let's do that. My domain here, I would want 9 minus x squared minus y squared to always stay greater than or equal to 0. And the range, let's like take a look at the picture when we're done here. All right, so if I kind of cleaned up this domain right here, if I move the x squared and the y squared to the other side, I'd have x squared plus y squared. Let's turn around and get 9 over there. So I kind of like refigured it a little bit. If I move the x squared and y squared to the right and leave 9 on the other side, 9 is going to have the inequality open to it. So my domain, oh my gosh, my domain is basically all the numbers inside a circle of radius 3, right? And so you're going to see why that is in a minute. So sometimes with these problems, you have to kind of trick it a little bit to see what it was. So this is, remember, z. So I see it's a square root on the other side. So why don't we square both sides and see what happens? So I get z squared equals 9 minus x squared minus y squared. Well, if I put in the x and the y on the other side, I get x squared plus y squared plus z squared equals 9. So now I recognize that shape, right? That's a sphere with radius 3. But since it was solved for z, you know, for a sphere, I could have any one of like 6 things happen to me this way. For a sphere, I could have the top or bottom, because if I solve for z and I do the positive part, it's the top. If I do the negative, if this was a negative here, it would be the bottom half. Well, if I solve for y, I get the right side or the left side. If I solve for x, I get the front or the back. And so, you know, different pieces of the sphere, different hemispheres that you get. So anyway, this goes up to 3 here. It goes 3 on each way. Let's try and draw it the best we can. And it's basically coming down. I got this kind of circle here. And I have this hemisphere, this like little top of a sphere there. Okay, so the best you can do it. So also describe it. You know, you say to yourself, hey, this is the top half of a sphere with a radius 3. So your description plus your picture, okay? All right, so sketch this graph down here. So we forgot to tell the range. So my range here, I can tell you that nothing is going underneath the z-axis, right? So I'm staying basically from 0 to 3. So my range is from 0 to 3. All right. And you could also write your domain like more officially. You could say, hey, the domain is x's and y's such that, and then just say x squared plus y squared is less than or equal to 9. Okay, so down below here, looks to me like I could use anything for x and y. So my domain is all real numbers, any 2 real numbers that you want. All right, my range on the other hand, let's take a look. Whatever x and y are, I'm going to be doing 3 minus that. So best case or easiest case scenario, x and y are 0. So the highest I'm ever going to get is 3 because I'm always taking stuff away from 3. I'm always going under 3. So it seems like my range here, and we'll prove it by the picture, is everything from negative infinity up until 3. Okay, all right, so let's take a look. If this one, I can use my trace curves I did it earlier. So let's let x equal 0. So if I let x equal 0, I get z equals 3 minus y squared. So that's a parabola touching 3 on the z-axis. And if I let z equals 0 here, I would get 3 minus y squared. So I get basically y equals plus or minus radical 3. So it's going to be touching the y-axis at 1.7 on either side. So parabola coming down there. And then if I do the same thing for y equals 0, I get z equals 3 minus x squared. So same parabola, but now it's coming to the front. It's hitting here and back there. So basically we have a paraboloid, right? And you pick people who did that shape before, but we have a paraboloid, like circular paraboloid. Okay, and then you can see the domain and range in there. Okay, all right. So these are just some pictures of some different shapes. Nobody would ever make you draw these, but hopefully you can, see from the equations there, you can see the sine curves and all that kind of stuff happening there. Okay. All right, so level curves. So like we did trace curves before, we're going to be doing level curves here. And so one kind of interesting thing, this is Round Top Mountain. I don't know if you guys have ever been skiing. This is a topographical map of Round Top Mountain. And so something kind of cool to notice here, you have to imagine that like if somebody took this mountain and like pushed it down flat, but still wanted to know like how steep it used to be in all the different areas. So like if you were trying to, make a ski resort here, well, look right here. Those lines, you see how they're closer together? Like all these lines right here are really close together. That means that's a very steep part of the hill. Whereas over here, they're not so close together. So that's like a kind of like a not a steep part. So maybe you'd put your black diamond on the very steep part. So your black diamond would go here. But over here, you'd put your bunny slope or your green slope or whatever. I don't know if you've been skiing, but that's what they call them. Green slopes are like the easiest ones. So what does it mean when the curves are close together? It means that you have a steeper slope. Okay, so the level curves of a function of two variables are the curves with the equations f of x, y equals k. So k is a constant. So we just kind of pick, instead of 0, we pick things like, pick a 5, pick a 2 or whatever. So we'll do that in a minute on the next page. Okay. All right, so when you have like a contour map like you have here, I'm trying to find f of 1, 3. So if I go to 1, 3, it's right there. That looks closer to the 70 curve than the 80 curve. So I'm going to say it's like 73. All right, so that would equal, we'll say 73. All right, f of 4, 5. So 4, 5 is like right here. Looks a little closer to the 60 than it does for the 50. So maybe I'll say it's 56. All right, and so this is just these little red curves here, and the little loops and the numbers with them are indicating like the height, the z value, because remember we pushed it down flat so we can kind of like see what's going on. All right, so we're going to sketch the level curves of these two functions below. So remember with level curves, we start off with the different values for k. So we're going to sketch it over here. All right, and I don't know, we'll start off with k equals 0. All right, so k equals 0, I get 0 equals x3 minus y. So y equals x to the third. All right, so I have like a cubic function. Okay, let's let k equals 1. So I would get 1 equals x3 minus y. So y equals x to the third minus 1. So another curve, same thing. Okay, and so then, k equals 2. I'm going to get y equals x to the third minus 2. So starting at 2 and then curving there. Okay, so a bunch of cubic functions. Well, look what happens when I look at my 3D graph and look at that problem. So my x-axis is my my red one, okay? And so like, look, there was my curve there. And so look at those curves right there kind of going all along. Oh, hang on, I want it like this, I'm sorry. X is positive on that side. So look, those are all those level curves right there. Just kind of crossing along the y-axis there. And, but you see how basically it looks like a cubic function, but it's just traveling in kind of a different way. All right. So over here, this one's going to be a little bit crazier here. And if I set it equal to 0, then it's not really going to do me any good. So I'm just going to use I'm going to use k equals 1. Okay. All right. So we're going to use k equals 1. And then I'm going to just kind of tell you about what would happen if I let it equal to different numbers. So if I use 1, I get 1 equals y over x squared plus y squared. So cross multiply, x squared plus y squared equals y. I'm going to move the y over so I can complete the square. And so actually, yeah, no, that's fine. All right, so half of 1, because it's 1y, half of 1 is a half. 1/2 squared is a fourth. So I'm going to add 1/4 here and add 1/4 on the other side. So I get x squared plus, and if I factor that back, I get y minus 1/2 squared equals 1/4. All right, so basically what I have right here is I have a circle. I have a circle with the center at 0 and 1/2. So the center is at 0 and 1/2, but the radius is also 1/2, the square root of this 1/4 right here. So the radius goes here to here and here to here. So it's like a little circle there. So what's going to keep happening as you let k increase, you're going to get another circle. Let's say that your circle, let's say the center of the circle was now at 1. Well, the radius is also going to be 1. And so you're going to get a circle here. And let's say the circle was at 2. And then the center was at 0, 2. Well, the radius is also going to be 2. So it's going to come around and go like that. All right, so it's always going to be inside of itself like this. And there's nothing to say that k could be positive. It could be negative as well. So if it was negative, it would produce the same picture, but down below. Okay, so when I show you the picture of this, you'll kind of see why. So, and again, this one would be like kind of a little bit too hard to do, but you can see it here on the picture. So look at those. If you were to flatten this shape right here, you see all those circular pieces like rising. They're really tiny in the middle, and then they're getting fatter as they get closer to the XY plane. And so basically, if you flatten this, that's what it would look like. All right. So these are just some more pictures that you can see. Like these are basically, this is their level curves right there. And so basically level curves very close together indicate a surface that is very steep. Okay. All right. And we can also do this with, you have like a fourth dimension. So basically if you have x, y, and z in your equation, then f of x, y, z is your function. And so a lot of times they'll use like the letter W for this or what have you. So basically if I wanted to do the domain of this thing, I would say, hey, it's x, y, and z values such that, and the only thing restricting me here, I can do the sign of anything, I can multiply by anything, but this piece right here, z minus y, has to be greater than 0. It can't even be equal to 0. You can't do the log of 0, you can't do the log of a negative. Okay. And the last thing right here, if you have the level surfaces, so we were doing level curves because if we have a function of xy and has xy in it, you're going to get a level curve when you set your function equal to a constant. Well, if I set this equal to a constant, I'm going to get something like this. 1 equals x squared plus y squared plus z squared. So no longer is my trace thing a curve. It's now a surface because look, it's that little ball, a sphere right inside the middle. If I let the k value equal to, let's say, 4, then I get another sphere with the radius of 2. And so I get another sphere in the center right there. So it just increased your item inside. It increased the value of it. So before we were getting curves, so now we're getting surfaces because now what we're putting in is a 3D item. Okay. All right, and don't do this homework down here. We are going to give you some class time. I'm going to give you some class time to do that next class. Your job tonight is just to take these notes. I'll see you in class.